Hello, my name is Paul Hudson and I've written lots of books about Swift. For example, Hacking with Swift, Pro Swift, Hacking with macOS, Server-Side Swift and more. Don't worry, this video is not here to try and sell you books. So if you want more information, see the website, hackingwithswift.com, or follow me on Twitter, I am @2straws. This video is called Natural Swift, and it's designed to try and teach you to code Swift in a natural, idiomatic way. Python developers are used to the concept of Pythonic code, the kind of Python code an experienced developer would write, taking full advantage of the language so their code is clear and concise. Now in Swift, we usually talk about code being Swifty, with more or less the same meaning, taking advantage of the huge range of Swift functionality and Swift syntax to write clear, efficient, maintainable code. There are lots of things in Swift that make for good, idiomatic Swift code. For example, you might say guard and defer statements. You might say using optional safely rather than force unwrapping. You might say using for case let in loops, and so on. There are lots of examples you could choose. But in this video, I've picked out just 3 things I want to focus on. And I've chosen them not because they are the most Swifty things, but because they offer the most scope, I hope, for you to learn something new. Plus, they also combine together beautifully, so the whole is greater than the sum of its parts. So, the 3 things we're going to focus on in this video are, firstly, value types. What are they, and how they work, and how they differ from reference types. Secondly, functional programming. It really can work to make your code simpler and smarter. And third, protocol-oriented programming. Now we'll cover them in that order, 1, 2, 3, because I've arranged them easiest to hardest. So if you find the next few minutes far too easy for you, please stick with me. The difficulty definitely ramps up. We're going to start with something really easy. Value types versus reference types. Value types are things like strings and numbers. You can compare them if they conform to the equatable protocol. And it doesn't matter how they were created as long as they have the same value. For example, hello is equal to hello, and 5 is equal to 2 plus 3, even though one was typed directly and the other was created using addition. Swift relies extremely heavily on value types. In fact, almost all the core data types are value types. 2 are not: classes and closures. Classes you'll probably already know, as the debate between value types and reference types is often framed as classes versus structs. If you're not familiar with the difference between value types and reference types, let me walk you through a simple piece of code. Here is some Swift code modeling the end of the original Star Wars movie, A New Hope. First, we create a target, then we point that target towards the Death Star. If you remember the movie, you'll know that Luke Skywalker takes on the Death Star in his X-Wing, looking for a flaw in the exhaust port. He wasn't alone though. He had some other rebels with him, including Wedge Antilles. In the film, Wedge's X-Wing gets hit, and he has to pull away from the attack and return back to the rebel base. In code, we can model that by pointing the target toward the rebel base, then assigning it to Wedge. Now at the end of this code, what do you think Luke and Wedge would say when you ask them their target? The answer is we can't tell from this code alone. What happens depends on whether target is a class or a struct. The difference is just one word. In the latter one, you'd have some very confused cinema goers. Let's look at it again. If target is a class, it's a reference type, which means any instances of that class get shared between objects. So here it would mean that Luke.target and Wedge.target both point to the same target object. So when you change Wedge's target, you're also changing Luke's. That means Luke will start his attack run on the rebel base, rather than a Death Star, hence the confused. Cinema goes. On the other hand, if target were a struct, then it's a value type, which means it gets copied when assigned. When target gets assigned to Luke, he gets his own unique copy. This means the next line, target.location equals rebel base, doesn't change Luke's copy. He'll continue attacking the Death Star. And when we assign the target to Wedge, he gets his own unique copy too. Your view controllers normally hold properties to their children, and the children have delegates pointing back to their parent. Each time you pass an object around, you create an implicit relationship. You might even occasionally call straight back to the app delegate, and that's if you're lucky. If you think about it, it's remarkably easy to get into a situation where everything can change anything else. We choose not to change everything else, but it's programmer choice. This means you can give a doctor an array of patients to work on, but at any point another doctor can come along and change one of the patients from under their feet. This is not possible in Swift, or at least not easy. Array types are value types. So here we create an array called A and create a second array called B by copying A. After appending another number to A, the count of B is still 3. It hasn't changed just because A has changed. They are independent copies automatically. You might think that means a lot of copying. If two view controllers use the same array, they'd both take a copy of it. Objective-C worked around this by taking copies of objects no matter what, which was very wasteful. And Swift has a better solution. Multiple objects can point to the same value type as long as they don't try to change it. If they do make a change, Swift makes a copy at that point, so that no one else is affected. It's called copy on write. This can happen as often as needed. If no one else is affected, Swift will make the change in place. So you get safety and speed at the same time. So when you use value types, each piece of data has only one owner. No one else can change them. They aren't shared like references. This means you have no surprises. Your data can't be changed out from under your feet. It also means no defensive copying. That's the formal name for what Objective-C does, where you need to take a copy of everything to make sure you have true isolation. Objective-C even has a special copy attribute for properties to make this easier, but the workload is still there behind the scenes. This simplicity brings 3 further benefits. Without all the complexity of shared ownership, value types make your code easier to write tests for because everything is designed to work in isolation, so your tests become trivial. Your code becomes easier to debug because you know exactly who owns what data and can be sure it won't be changed in some random thread. In fact, you eliminate a whole class of race conditions from your code when you use value types, which is huge. All this combined means your code is easier to reason about, by which I mean to think through in your head and understand clearly. You've removed a lot of the potential for spaghetti code, and have the ability to simplify your whole app. Now, before I continue, I should say that reference types still have a part to play. They are used extensively in all of Apple's platforms because all their core framework are classes rather than structs. This means they expect to receive objects. Using things like NS coding to save your instance data just won't work when you try to force in a struct. You need to use the right tools, which in this case is a class. And in fact, classes have some benefits that can be useful. Creating class hierarchies, for example, is the root of our layouts. UI button inherits from UI control, which inherits from UI view, which inherits from UI responder, which inherits from NS object. I'm not saying class hierarchies are a great solution, and indeed shortly we'll be looking at alternatives, but I think it's important to remember they are pretty fundamental to Apple development. Another important feature of classes is that they support a dinit method, which automatically gets called when an object is being destroyed. This does not exist on structs, so if you need to take some sort of action when your instances are destroyed, you might consider using classes. Of course, the flip side is that structs get an automatic member-wise initializer, whereas classes require you to write your own. So go ahead and use classes when they're needed. The difference is that you're using classes deliberately rather than just as default behavior. By using a class, you're making a statement. I need some code to be run in dinit, or I need to extend a base class, or I want this data to be shared in multiple places. Because sometimes you do want your data to be shared, and that's okay. Just do it carefully. So, by using objects only when necessary, it makes clear your intent. I've chosen a class for a reason. This is important, and it's something we'll be coming back to again and again in this video. Clarity of intent matters. It means your code is easier to read for yourself and others. Now, There is an alternative here called boxing and unboxing, and I want to explain that a little more. Once you understand value types and reference types, it's much easier to choose between a class and a struct, at least at first. But as your application grows, you might find your situation becomes less black and white. Your app might work 95% of the time with value types, but maybe once or twice, everything would have been a whole lot easier if you had a reference type instead. All is not lost. Bearing in mind everything I've said about the pros and cons of both, there is a way to share value types in several places if you're convinced it's the right solution. The technique is called boxing, not the punchy, sweaty sort of boxing, but as in placing something inside a box. This approach wraps a value type inside a reference type, so you can share it more easily, and is commonly seen in languages like C# and Java. Now, I'm not going to continue repeating the warning that sharing rather than copying values raises the complexity of a program. Please just remember that yourself. So, let's walk through a practical example so you can see for yourself how it works. First, here's a person struct. We'll say struct person, then have three properties: var name, string, then var age, int, then var favorite ice cream, string. And we'll go ahead and create an instance of that. We'll say let Taylor equals person, name Taylor Swift, age 26, favorite ice cream, chocolate. If we want to share that Taylor struct across multiple objects, we'd create a person box class like this. Final class person box, var person, person, then init, person, person, and inside that, self.person equals person. Then close the brace and close the brace. Because we can create that box, we'll say let box equals person box, person, Taylor. Now that is a class container around the person struct, and as a reference type will be shared rather than copied. To demonstrate that, let's create a test container class that simulates some parts of your app, like different view controllers. So we'll say final class test container, then var box person box exclamation mark. So it'll start off being nil. Then we'll create two containers. We'll say let container 1 equals test container, then let container 2 equals test container. Then we'll write container 1.box equals box and container 2.box equals box. So that creates two containers, each of which point at the same person box object, which in turn means they're pointing at the same person struct. To prove this works, we could write some code like this. Print container 1.box.person.name, print container 2.box.person.name, then box.person.name equals not Taylor, and again print container 1.box.person.name and print container 2.box.person.name. That'll print Taylor Swift twice, then not Taylor twice, proving that changing the value in one container changes the value in the other. If you intend to make extensive use of boxing and unboxing yourself, again, warning, 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 dangerous, so forth, you might want to consider creating a generic box class, more like this. Final class box t, var value t, and init value t, self.value equals value. And now we can modify test container. We could say instead, final class test container box, var box, is a box of type person, like that. That way you can share other types of structs without having to have lots of different box classes around them. Now, it's undeniable that this approach weakens the power and safety of value types a little bit, but at least it makes explicit which situations give you the safety of value types and which don't. You're stating, this bit, this is explicitly shared, rather than implicitly sharing everything. Value and reference types also differ in the way they handle immutability, but I've kept it separate because it's quite a subtle difference and it's easy to get confused. Let me backtrack a little. One thing I love about Swift is that it's aggressively focused on immutability. That is, it's very easy to say, don't let this value ever change. Not only does this mean you're encouraged to use let rather than var when writing your own code, but the Swift compiler will scan your code and warn when it finds places where variables could be made into constants. This is very different from Objective-C, where immutability was enforced only as part of your class name. NSString had an NSMutable string counterpart. NSArray had an NSMutable counterpart. So, immutability and value types might seem to go hand in hand. All of the values to the value, they change. Integers are value types in Swift. And you can't exactly say, hey, I'm changing number 5 so that 5 is actually equal to 6 now.
Oh.
When you start comparing classes and structs, the immutability is more complicated, and I want to explain why. Consider the following code. Struct person struct, var name string, var age int.
Ну да.
Create one of those things.
Он колет, он сегодня уже нахуй, знаешь что?
Name Taylor
Типа, может, в натуре Коля нахуй размотать.
change that. Taylor.name equals Justin.
Не.
When that
Ну,
code runs, the
ну,
final name value of Taylor is which is going to be
ну.
a huge surprise for any Swift concept. If you
Да я
change
ебал
just
рот.
one line of code,
Зачем?
will be let Taylor equals with just one line of
Это
code
пизда.
won't even compile.
Так и нахуй, ну типа, блядь, знаешь это? Он нахуй, ну реально нахуй гонит. В плане, что нахуй, братан, он нахуй, ну типа, короче. Допустим, сегодня что-нибудь с ним споришь, а сейчас, не помнишь, что я позвонил? Он мне начал говорить, нахуй, да я ничего не записывал. Я говорю, ты что, говорю, блядь, из меня, нахуй, сейчас, говорю, долбоеба делаешь. Он, а? Да. Не знаю, нахуй, у меня же, блядь, мамка, нахуй, разошлась же с кем-то, нахуй. Ну его ж. Да ну нахуй. Не, я имею в виду, нахуй, я как понимаю, там Яшку завалили, нахуй. И вот он, нахуй, отец настоящий. Не то, не этого, нахуй, не Яшкин сын, нахуй, короче. Тот-то, блядь, нахуй, Яшка-то от того Васи, который последний был, которого ёбнули по подъезде, нахуй. Вот. Но это же Яшкин, блядь, отец. У него есть свой батя, нахуй, настоящий, ну понял, с кем мамка у него разошлась, нахуй, понял. Потом он начал с Яшкой жить. Понимаешь? А. Не, нет, ты в этом плане, нахуй, не. Я тебе говорю, просто нахуй, я ебал рот, нахуй. Ну типа, что нахуй, либо ты споришь, короче, потом. И потом он нахуй не помнит. Блять, нахуй. Да, я сегодня с утра вообще охуел, нахуй, на машине подъезд открыл, нахуй, просто вообще. Я охуел, нахуй. Then Taylor 3.name equals Justin Bieber, and Taylor 3 equals person class, name Justin Bieber, age. Both of those are perfectly fine. Finally, a constant object. This is where you'll see that changing property is okay, whereas changing reference is not allowed. We'll write let Taylor 4 equals person class, name Swift, age 6. Taylor 4.name equals Justin Bieber. Не удивлюсь, но понял. Name Justin Bieber, age 22. That's not okay. As you can see, the difference occurs where constants are used. A constant object cannot be changed. Блять, братан. Can change any different whereas a constant struct the most common place where mutability is concerned is when dealing with collections like arrays. These are value types in Swift, but they can also be mutable. You can add and remove elements freely if you declare them as var. If you're able to, ну, блять, нахуй, пиздец, нахуй. Ты еще, нахуй, этого Коля, блядь, его не видел, я вообще охуел, герой России, блядь, нахуй. Я говорю, ты где медаль тогда, дебил? Вот, да, на площади стоял, мне выдали. Я говорю, ты это, нахуй, ты слушай, слушай, я говорю, ты хоть застрелил там кого-нибудь? Да нет, я не смотрел. Я говорю, а ты стрелял? Да, стрелял. А как ты, блядь, стрелял, нахуй, я не видел, куда попадаешь? Да нет, я так вот, нахуй, пистолет, ну, типа, с автомата, сверху. Я думал, маленький пиздит, понял. Он мне накидывал, что он, типа, да он не был, нахуй. Да я, нахуй, не подгоняйся, просто, нахуй, братан. Да он...
Я ему нахуй говорил, что ну нахуй не нужен, братан. Да с чем связались, блядь? Еще раз говорю. Ты меня слышишь, нет? Я тебе говорю, что нахуй, он его нахуй понял, сейчас лето, ну типа зимой нахуй понял, он там нахуй исполнял, я ему говорю, нахуй он тебе нужен, этот Коля, он долбоеб. Он, да нет, такого не может быть, да это вот, нахуй, он так не может. Я ему, блядь, нахуй все по полочкам разложил, он нахуй, блядь, да мне не поверил, понял. Все, потом дальше больше, второй раз понял, короче, мочит у него уже, нахуй, понял. Я говорю, мне похуй, это твой друг. Он его Вася прощает, нахуй, уже 8-й раз, нахуй, понял. И каждый раз, нахуй, думаешь. Я не про это. Он его...
Andy is an experienced functional developer, but he's also pragmatic about learning approaches. I really hope he won't frown too much on simplifying and even jettisoning so much of the theory. Functional programming, or at least slightly simplified definition,
Понятно, это.
can dramatically simplify
Ты что, дома, все?
and, as you'll
Наш кож спать либо. Да не, это типа про другой говорю, что он нахуй понял, плачет нахуй от того, что ему, сука, обидно нахуй, то, что этот олень его, ну понял.
at first this will
Ну все, дура нахуй, наигранный, он реально рыдает нахуй, сидит нахуй каждый день. Там через день нахуй нахуярится, потом позовет его нахуй, понял. Под кровь ему, сука, залезет нахуй, понял. Я тебя не прощу никогда, как будто нахуй, знаешь, это, с Машей нахуй ругается, я тебя никогда не прощу, вот иди нахуй, бля. Вася, вот ты когда сказал семейная ссора, понял, Вася, это пиздец. У меня просто язык не поворачивался, понял, как пиздануть. Ну это так, нахуй, понял, как будто нахуй это его тёлка, нахуй, понял, которая, блядь, нахуй, точнее он тёлка, нахуй, которая говорит, я тебя не прощу, нахуй, понял. Ну, блядь, я ему как бы пытался без меня, нахуй, это сказать. Ну, фу, блядь. Надеюсь, нормально все будет, мне похуй, блядь. Вот. Мне надо, из него надо пылесос, братан. Да. Мне надо пылесос, нахуй, блядь, отнести ему, он до сих пор варенье, блядь. Я ж взял. Все, давай, спокойной ночи, кутышка.
and return back an array of integers based on the length of each string, that function returns 6, 4, 5 when given a Taylor for a demo. It doesn't matter what else happened in your code or how often the function is called, the same input must return the same output. A corollary is that functions ought not to create side effects that might affect other functions. For example, if we had another function, fetch system time, that returned the time, it should not be the case that calling fetch system time could affect the result of length of strings. A function that always returns the same result for a given input without causing side effects is often called a pure function. One source of confusion about pure functions revolves around the meaning of side effect. If a function does something like writing to disk, is that a side effect or in fact just the main point of the function? There's a lot of argument about this, and I'm not going to wade into it. Instead, I'll say that functional coders should aspire to create pure functions. When it comes to the crunch, favor predictable output for known input over avoiding side effects. That is, if you want to create a function that writes data to the disk, go for it, but at least make sure it writes exactly the same thing when given the same data. Fourth, because functions always return the same output for some given input, we should prefer to use immutable data types rather than using functions to change mutable variables. I've already talked about the importance of immutable data types and values rather than references, so I shan't go over them again. Fifth and finally, because our functions don't cause side effects and variables are all immutable, we can reduce how much state we track in our program and often eliminate it altogether. The lack of state can be tricky at first because it's so deeply baked into object orientation. State is a series of values stored by your program, which isn't always a bad thing. It includes caching things to increase performance, and also important things like user settings. The problem comes when this state gets used inside a function, because it means a function is no longer predictable. Using the length of strings example from earlier, consider what would happen if we had a Boolean setting called return lengths as binary. The function that would always return 645 when given Taylor, Paul, Adele could now also return 110, 10, 101, depending on the value of something completely external. Being pragmatic, don't try to avoid state at all costs, but never let it pollute your functional code, and work to minimize its use more generally. When all 5 of these principles combine, you get a number of immediate, valuable benefits. When you write functions that produce predictable output, you can write unit tests for them trivially. When you use immutable values rather than reference types, you remove unexpected dependencies in your app and make your code easier to reason about. And when you build small, composable functions that can be combined with higher order functions and reused in any number of ways, you can build hugely powerful apps by putting together many small, simple pieces. Okay, so that's how functional programming works. It's time to look at real code. Specifically, we're going to look mainly at 5 methods: map, flat map, filter, and reduce. Once we're through with that, we'll look at using composition to build bigger functions from smaller ones. Let's start with the easiest way into functional programming, the map method. This takes a value out of a container, applies a function to it, then puts the result of that function back into a new container that gets returned to you. Swift's arrays, dictionaries, and sets have map built in, and it's commonly used to loop through every item in an array while applying a function to each value. I already mentioned a length of strings function that accepts an array of strings and returns an array of integers based on the size of the input strings, and you might write it something like this: func length of strings, string array, returns int array. Var result equals int array, then for string in strings, result.append string.characters.count, closing brace, return result, closing brace. That function takes an array of strings and returns an array of integers based on those strings. This is a perfect use for map, and in fact we can replace all that code with this: return strings.map $0.characters.count. That's it. And it's clear the functional approach is shorter, but its benefit is not just about writing less code. Instead, the functional version conveys significantly more meaning to the compiler. It's now clear we want to apply some code to every item in an array, and it's down to Swift to make that happen efficiently. For all we know, Swift could run the closure in parallel, so it gets applied to 4 items at a time, or it could run through the items in a more efficient order than beginning to end. Using map also makes clear our intention to other coders. This will go over every item in an array and apply a function to it. With the traditional for loop, you might have a break in there halfway through, something you can't do with map, and the only way to find that out is to read all the code. If you're following the 5 functional principles I already laid down, specifically using pure functions and avoiding state, a human reading your code can know immediately that a closure used with map won't try to store global state along the way. This simplification is important, and it's a change of focus. Javier Soto, the well-known functional proponent and Swift hacker extraordinaire at Twitter, sums up the usefulness of map like this: it allows us to express what we want to achieve rather than how it is implemented. That is, we just say, here's what we want to do with the items in this array, and that's easier to read, write, and maintain than writing loops and creating arrays by hand. One more thing. Notice how the type signature hasn't changed. That means we write func length of strings string array returns int array, whether or not we're using a functional approach internally. This means you can change the internals of your functions to adopt functional approaches without affecting how they interact with the rest of your app. You can upgrade your code bit by bit, rather than all at once. To help you get more comfortable using map, here are some examples. We could write some code to convert strings to uppercase by saying let fruits equals apple, cherry, orange, pineapple. Then let upper fruits equals fruits.map $0.uppercase. Or we could write some code to convert an array of integer scores into formatted strings. Let scores equals 100, 80, 85. Then let formatted equals scores.map your score was $0. We could write code to use a ternary operator to create an array of strings, matching each integer item against specific criteria. So using the same scores array of 100, 80, 85, we could write a new constant, pass or fail, to be scores.map $0 is greater than 85, question mark, pass, colon, fail. So if the value is greater than 85, it'll be pass, otherwise it'll be fail. We could also use Swift's range matching operator tilde equals to check whether something's in a range or not. We could have a new array, let position equals 50, 60, 40. Then let average results equals position.map 45 ... 55 tilde equals $0 question mark with an average colon outside average. That means is if the value is between 45 and 55 inclusive, return with an average, otherwise return outside average. Finally, an example of using map with an external function. We can use square root, sqrt, to calculate the square root of numbers. We could say let numbers colon double array equals 4, 9, 25, 36, 49. Then let result equals numbers.map square root. As you can see, map has that name because it specifies the mapping from one array to another. That is, if you pass an array ABC and function f, Swift will give you the equivalent of FA, FB, FC. I'm not going to lie to you, flat map can seem daunting at first. I put it here, directly following the surprisingly easy and useful too map function, because the two are closely related, not because I want to shock you with flat map so early in your functional career. As you saw, map takes an item out of a container, like an array, and applies a function to it, then puts it back in the container. When an array contains an array, i.e. an array of arrays, you get access to a version of the join method that converts the array of arrays into a single array, like this. Let numbers equals 1, 2, 3, 4, 5, 6. Then we can write let joined equals array numbers.joined. That will return 1, 2, 3, 4, 5, 6 as a single array. So joined reduces array complexity by one level. A two-dimensional array becomes a single-dimensional array by concatenating items. The flat map function is effectively the combination of using map and joined in a single call, in that order. It maps items in array A into array B using a function you provide, then joins the result using concatenation. It also automatically strips out nil values at the end. First, let's look at our friend map. We'll say let albums optional string array equals fearless, nil, speak now, nil, red. Then we'll say let result equals albums.map $0 and print result. Now mapping using $0 just means return the existing value. So that code will print optional fearless, nil, optional speak now, nil, optional red. That's a lot of optionals, with some nils scattered throughout. Switching to flat map rather than map can help. So we'll change map to be flat map, otherwise still $0. Just changing map $0 to flat map $0 changes the result dramatically. We now get fearless, speak now, red. The optionals are gone and the nils are removed. Perfect. The reason for this magic lies in flat map's return value. Whereas map will retain the optionality of the items it works on, flat map will strip them out. To show this off, let's try writing the code side by side. Let map result equals albums.map $0, then let flat map result equals albums.flatmap $0. Now using code completion, you can see that map result is of type string ? Optional string, and flat map result is of type string non-optional. If the usefulness of flat map isn't quite clear yet, please stick with me. Let's look at this example again. Let album string ? equals fearless nil, speak now nil, red. Let result equals albums flat map $0, print result. The albums array is of type string ? so it holds an array of optional strings. Using flat map here strips out the optionality, but really that's just the effect of joining the optional containers. It doesn't do any sort of mapping transformation. Now here's where flat map becomes awesome. Because the joining happens after the mapping, you can effectively say, do something interesting with these items, map, then remove any items that return nil, join. To give you a practical example, imagine a school grade calculator. Students are asked to enter their scores for various exams, and it will output their estimated grade. This needs to convert user-entered numbers into integers, which is problematic. They can make mistakes or enter nonsense. As a result, creating an integer from a string returns an optional integer. It's nil if the input was fish, but 100 if the input was 100. This is a perfect problem for flat map. We can take an array like 100, 90, fish, 85, then map over each value to convert it to an optional integer, then join the resulting array to remove the optionality and any invalid values. So we'll write let scores equals 100, 90, fish, 85. Let flatmap scores equals scores.flatmap int $0. And finally print flatmap scores. As you can see, outputs 100, 90, 85 as numbers. Perfect. This technique can be used whenever you have to differentiate between success and failure of code by the use of optionality. Put that more simply, if you have an array of input items and a transformation function that will return either a transformed item or nil if the transformation fails, this technique is ideal. If you think the situation crops up rarely, remember that any throwing function can be used with try question mark, which translates it to a function that returns nil on failure. Exactly what this approach means. Now obviously I can't predict what's in your code, but here's an example to get you started. Let files equals 1.10.flatmap, try question mark, string, contents of file, some file $0.txt, then print file. That will load into an array the contents of some file 1.txt, some file 2.txt, and so on. Any files that don't exist will throw an exception, which try question mark converts to nil, and flatmap will ignore, all with just one line of code. So, try question mark effectively turns any throwing call into a candidate for flatmap by introducing nil. A similar trick is possible using the as question mark typecast, which also returns nil when it fails. For example, if you wanted an array of all the UI kit labels belong to the current view, you could write this. Let labels equals view.subviews.flatmap $0 as question mark UI label. That will attempt to typecast each subview as a UI label and place any item that succeeded into the returning array. Even better, Swift is smart enough to infer that the labels constant is an array of UI labels. As you can see, flatmap brings together join, map, and filter for nil values all in one, and I hope you can see how useful it's going to be in your own code. The filter method loops over every item in the collection and passes it into a function that you write. If your function returns true for that item, it'll be included in a new array, which is the return value of the filter. For example, this next code creates an array of the first 10 items in the Fibonacci sequence, then filters that array to include only items that are even. So we can write let Fibonacci numbers equals 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Then let even Fibonacci equals Fibonacci numbers.filter $0% 2 equals 0. So that code will run and pass number 1 into the closure, making 1% 2 equals 0, which is false. As a result, 1 will not be included in the result array. When it reaches 2, that will be included because 2% 2 equals 0 is true. As with map, the order items are filtered is out of your control. Swift is free to apply any optimizations it wants to make filtering go faster. Let's look at some examples that show off using filter in different ways. First, let names equals Michael Jackson, Taylor Swift, Michael Caine, Adele Atkins, Michael Jordan. Then, let result equals names.filter $0 has prefix Michael. That creates an array of strings using only names that begin with the word Michael. So in this case, Michael Jackson, Michael Caine, and Michael Jordan. Or we could create a subset of the words array based on which word exists in the string input. So we can say, let words equals 1989, Fearless, Red. Then let input equals my favorite album is Fearless. Finally, let result equals words.filter input.contain $0. I've already shown off flatmap's extraordinary ability to strip nil values from an array, but it also removes optionality from the remaining elements. So if you want to strip nil but retain optionality, you'd use filter like this. Let words optional string array equals 1989 nil, fearless nil, red. Let result equals words.filter $0 is not equal to nil, print result. The reduce method condenses an array into a single value by applying a function to every item. Each time the function is called, you get passed the previous value from the function as well as the next item in your array, and it's down to you to decide what to do with them. Probably the most common example of using reduce in Swift is with the addition operator, plus. You can say something like, let scores equals 100, 1995, let sum equals scores.reduce 0 plus. And that will make sum equal to 285 by adding 0, 100, 90 and 95. The 0 is the initial value, which is used the first time your function, in this case plus, is called. Once you become more experienced with reduce, you'll start to realize why functional developers lean on it so heavily. To make the behavior of reduce a little clearer, let's experiment with other possible uses. Try this code. Let result equals scores.reduce empty string $0 plus string 1. Those two lines of code operate on an array of integers, but it starts with an initial value of an empty string. The body of our reduce closure is $0 plus string $1, which means take the current string and add it to a string containing the contents of the current integer. When it first runs, the initial value, empty string, is used and added to 100 to give 100. The second time, 100 is added to 90 to make 10090, because string addition means append. The third time, it's 10090 plus 95 to give 1009095, which is the final result. It's time to see how well you understand reduce. I'll write some code, and I want you to fill in the gaps using reduce. We'll start off with let names equals Taylor, Paul, Adele, then your code here, and print count. And I want you to replace the comment with code to sum the number of characters used in all the names. It should print 15, which is the sum of the lengths of Taylor, Paul, and Adele. This is a straight integer operation, but you can't just use plus because you want to add the character count rather than appending strings. Give it a try now. My solution is to say let count equals names.reduce 0, then $0 plus $1.characters.count. For comparison, here's the non-functional variant. Var count equals 0, for name and names, count plus equals name.characters.count. Again, it's not really about the difference in the number of lines of code. Instead, it's about clarity of intent. With the non-functional variant, we're manipulating each item directly, and you have to read the contents of the loop to see what happens to count. It's a variable now, so it can be changed in any number of ways. Reduce could also be used to find specific values in an array, but you need to keep in mind there are often better solutions. For example, this next code will find the longest name in the array by comparing each name against longest so far. We can write let names equals Taylor, Paul, Adele, then let longest equals names reduce empty string $1.characters.count is greater than $0.characters.count. If true, $1, otherwise $0. That code certainly works, but you could use the max method instead, like this. Let longest equals names.max $1.characters.count is greater than $0.characters.count. In this example, reduce will do one extra comparison because of the initial value of empty string. However, because you're starting with something, you're always guaranteed a value to work with. In comparison, max returns an optional value that you then need to unwrap. So which you use will depend on your context. Earlier I said the reduce method condenses an array into a single value by applying a function to every item. That's true, but it might mean a bit more than you realise. The input can be an array of anything, and the output can be any kind of value, even another array. To demonstrate this, I want to use reduce to convert an array of arrays, a two-dimensional array, into a single array. To make this work, we have to provide reduce with an initial value of an empty array. Then each time it's called will add the new item, another array, to the existing one using plus. So the code is this. Let numbers equals 1, 1, 2, 3, 5, 8, 13, 21, 34. Let flattened int array equals numbers.reduce empty array $0 plus $1. Then print flattened. Again, that code certainly works, but it could be more succinctly expressed by using flatmap like this. Let flatten 2 equals numbers.flatmap $0. You can even use joined like this. Let flatten 3 equals array numbers.joined. The moral here is that as your functional arsenal grows, you'll find several ways of solving the same problem, and that's perfectly fine. The second and third of my 5 functional principles are to use higher order functions and make your functions pure if possible. The combination of these two allows us to build new functions by composing, i.e. putting together, existing functions. This comes in 2 forms: simple chaining, i.e. running one pure function and piping its output into another, and true functional composition, which is creating new functions by assembling others like Lego bricks. Each approach is commonly used, so I'll cover them both. Chaining really is very simple, so we'll start with that. If you can use map, flat map, filter and so on, then chaining them is just a matter of making one call, then immediately making another. First, let's write some example data for us to work with. We'll create an array of tuples containing basic data about some cities. So we'll say, let London equals name London, continent Europe, population 8.539 million. Then let Paris equals name Paris, continent Europe, population 2.244 million. Then let Lisbon equals name Lisbon, continent Europe, population 530,000. Let Rome equals name Rome, continent Europe, population 2.627 million. And finally, let Tokyo equals name Tokyo, continent Asia, population 13.35 million. We'll put all those into an array by saying let cities equals London, Paris, Lisbon, Rome, Tokyo. To sum the population of all cities, you'd use reduce like this. Let total population equals cities.reduce 0, $0 plus $1 dot population. To sum the population of cities in Europe, you need to run filter first, then change to reduce like this. Let Europe population equals cities.filter $0.continent equals Europe dot reduce 0, $0 plus $1 dot population. To print formatted information about the bigger cities, we can use filter to select only cities with high population, call sorted on the result, use prefix to select the first three items, use map to convert the city tuples into a formatted array, then use join to create a single string. So we'd write, let bigger cities equal cities filter, $0 population is greater than 2 million, sorted, $0 population is greater than $1 population, prefix up to 3, then map, $0 name is a big city with a population of $0 population, and finally joined, separator, \n. Now clearly there soon comes a point where chaining functions together becomes hard to read. Probably anything more than 3 will cause more confusion than it clears up. Once you have a collection of small reusable functions in your code, you can create new functions by assembling existing ones in specific combinations. This is called function composition, and I hope it will encourage you to ensure your functions can be composed easily. Swift does not have a compose operator, i.e. a special operator that makes function composition easy, so most people combine functions like this. Let foo equals function C, function B, function A. Some functional coders create a special compose operator using 3 right angle brackets or similar that allows you to rewrite that code a little more clearly. Let foo equals function C, function B, function A. I personally don't find that particularly pleasant to read, but you still have to read right to left. Instead, I prefer to create a custom operator that lets you write code like this. Let foo equals function A, function B, function C. And it's not hard to do using operator overloading. I'll show you the code and explain how it works. First you write precedence group, composition precedence, associativity, left. Then infix operator, angle bracket, angle bracket, angle bracket, composition precedence. And now for the line noise, brace yourself for this. Func, bracket, 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 TUV, LHS at escaping, T returns U, RHS at escaping U returns V, and the whole thing returns T, it returns V. And inside there we write return RHS LHS $0. So that declares a new operator, 3 angle brackets, which uses 3 generic data types, T, U, and V. It works with 2 operands, LHS and RHS, which are 2 functions. LHS accepts a parameter of type T and returns a value of type U, and RHS accepts a parameter of type U and returns a value of type V. The whole function returns a new function that accepts a T and returns a V. It just merges the 2 steps by calling RHS LHS $0. Both functions must be declared at escaping, because we're creating and returning a new closure that will call them later. To make things a bit clearer, imagine our first function accepts an integer and returns a string, and the second function accepts a string and returns an array of strings. That would make the function look like this. Func bracket 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 LHS at escaping accepts int returns string, RHS at escaping accepts string returns array of strings. And the whole thing returns a function that accepts an int and returns an array of strings. Inside there again, return RHS LHS $0. Hopefully that makes this behavior a bit clearer. By combining the two functions together, the resulting combined function accepts an integer, the input for the first function, and returns an array of strings, the output of the second function. Now this operator is just syntactic sugar, but let me give you an example that demonstrates how useful it can be. Consider the following code. Func generate random number, max int, returns int. And this will just do let number equals int, arc4 random uniform, uint32 max, and print out using number, and then return it. Then we'll have a function called calculate factors that calculates the factors for a given integer and returns an array. So we'll say func calculate factors for number int, returns int array. Then return 1 ... number filter number %0 equals 0. And finally we'll have a reduced to string function that takes an array of integers and returns a single string. And inside that we'll write return numbers.reduce factors $0 plus string $1 plus a string with a space in. When called in a sequence, those functions generate a random number, calculate its factors, then convert that factor array into a single string. To call that in code, you'd normally write this. The result equals reduce the string, numbers, calculate factors, number, generate random number, max 100, and then print the result. That needs to be read from right to left. Generate random number is called first, then its return value is passed to calculate factors, and its return value is passed to reduce the string. And if you need to write this code more than once, you have to make sure you keep the order correct, even when making changes in the future. Using our new compose operator, there's a better solution. We can create a new function that combines all three of those, then reuse that function however we need. For example, let combined equals generate random number, then calculate factors, then reduce the string. And we can write print combined 100. There are several reasons I love this approach. First, it's read naturally. Generate a random number, calculate factors, reduce a string. Second, it lets you save the combined function for use as many times as you need. Third, you can compose your functions even further. Combine can be used with the same function to create an even bigger function. And fourth, the combined function automatically accepts the same parameter as the first function that was composed. So we use combined 100 rather than just combined. I hope this technique gives you another good reason to write small, modular functions. You can write as many as you want, each one performing one small task, then create larger functions that combine those together in useful ways.
Okay, enough about functional programming. I hope I've managed to convince you it has something to offer everyone. And even if you want to take a few concepts, that's still a big improvement. Now, if you look back at the original plan, you'll see we've now finished value types and we've finished functional programming. So it's time for the final topic, protocol-oriented programming, otherwise known as POP. Now I'm going to explain POP to you by starting with OOP, object-oriented